Hi, everyone. It's great to be here. So the paper I'm presenting today is Fair Classification with Partial Feedback, and this is by two of my students, Vijay Keswani and Anay Mehrotra. Anay is a current PhD student at Yale, and Vijay graduated last year, and he's currently doing a postdoc at Duke. So he's the one who really spearheaded this work, and he's on the job market. He's absolutely fantastic, so please do reach out to him if you're looking to hire. He was supposed to be here. Unfortunately, due to visa issues, he could not be here, so you're stuck with me. So my apologies in advance. Let's see. Nope. There we go. Okay, so as you have been seeing throughout this conference, there's many cases where we have some kind of prediction or classification domain, and we might have in particular collection of people, because in general what we're looking at are cases in which the social impact of our classifiers is really going to matter. So consider your favorite prediction or classification domain, and we'd have some kind of classifier that either positively or negatively makes a prediction about these people. And as you've seen throughout the conference, there could be many possible such domains, many applications. Often we think about things like predicting whether someone is going to default on a loan, to decide whether a bank is going to be giving them some kind of loan or lending some money. We might be thinking about something like disease prediction, where we factor in everything about a certain person, all of their symptoms, and see which type of diseases they might be susceptible to. Or perhaps something like recidivism prediction, where we're considering whether someone might recidivate in order to determine bail. So in all of these applications, in all of these settings, classifiers are already being used in the US and throughout the world to help, if not directly make decisions, at least inform decisions as to what happens to people. So in general, when we have one of these classifiers, again, we might positively or negatively make some predictions about people. And then they go through whatever process that is. So if we're talking about loans, they might receive or not receive that loan. If we're talking about disease prediction, we might determine, okay, we need to do some follow-up tests or not. And for recidivism, we might grant bail or again not, right? So a positive prediction means that we take some further action, and a negative prediction means that we don't. And what happens is that in all of these positive actions, those are the cases where we then get to observe true outcomes. So in any of these settings, we get to observe if we have a true positive or if we have a false positive, but our negatives we know nothing about, right? If you did not get that loan, we do not get to find out whether you would have repaid it or not, right? Similarly, if you did not get those tests, we have no idea what they said, and if you were not granted bail, we don't know whether or not you would have recidivated. So we end up with this kind of partial feedback type of situation. Now, when we have a partial feedback setting, the problem is because we only have data for those cases that were positively classified, that completely skews what information we have in the future. And I tend to think about this in the future, but really it tells us something about what we might have observed in the past as well. So the data that we use for our classifier to begin with is often already skewed because, again, a bank is not granting loans to everyone. It already is some sub-selection of people that have been granted loans or not in the past, and similarly for the other cases. So these past data sets lack information about those outcomes of any negative classified samples, right? And what that means is that when we look at our training distributions, we can't treat those as truth. They're misrepresented, they're biased, they're skewed. And unsurprisingly, that means that then we end up with errors in our classifiers, and errors that we don't even know well how to detect because we do not have that data to begin with. Now, we are, of course, not the first people to think about this or to observe this. There we go. So these type of errors have been observed in these three settings that I've mentioned so far, and in many other settings as well. And perhaps unsurprisingly to this crowd, these partial feedback errors disproportionately affect minority groups because of the inherent bias in many of these processes, right? So what we were hoping to think about is what kind of change can we make to an overall framework so that we can collect data while still remaining true to our original classification goals. So to do that, what we're going to focus on is, okay, let's actually take a step back first, and let's think about what happens in general when we have a partial feedback setting. So usually what we do is we think about kind of groups of applicants, so we do some kind of batch processes. So we have a group of applicants, and we say that they, submit their application, and at each iteration, we make some set of predictions, and once we receive those predictions, then we update our classifier, right? So this is generally how we might think of some kind of iterative setting. Okay, and prior work on learning when we have this partial feedback in these type of batch settings has certain drawbacks that make them not suitable for the types of applications that we really care about. So, for example, they might assume that you start off with an unbiased sample. So the diverse outcomes have already been observed when you start out, which is not always, or I would even venture to say often, not a good assumption in many of these settings. Another line of work would classify a large number of samples positively right at the start to basically learn more. So basically do a big round of data collection at the beginning, which does inform future rounds. So that might be a good step in terms of learning, but that might not be cost effective. That would be something like granting a whole batch of applicants alone and then using that information to learn from there, which may or may not be something that that a company would be willing to do. Or, kind of similarly to the first point, they might rely on strong assumptions on the accuracy of past decisions. So none of these things are generally true for the type of applications that we care about. So what we came up with is what we call kind of an exploitation framework that we can adapt to keep learning while also keep maintaining a high utility. So what we want is a high both cumulative utility and iteration-wise utility at every step of this process, but low disparate impact across the demographic groups. Okay, so this is kind of a high-level picture of our framework, and I'm going to walk you through it bit by bit. So the first thing that we're going to do is train a classifier. This actually works in general. Say train a fair classifier. That's the type of settings that I generally work on. The details of what is fair, which fair classifier, et cetera, is not what we're going to focus on here, right? This is basically a high-level framework that you can apply to many different situations. So plug in your favorite classifier, preferably fair classifier here, after you've talked to all the stakeholders, done all of the research, figured out what makes sense in your setting. But again, I'm not going to specify which one, right? So just think of this as a high-level framework that you can then adapt to your specific setting. So the first thing we're going to do is we take our data, admittedly biased, incomplete data that we have, and we train a type of fair classifier. So we make sure that this classifier maximizes the predictive utility, perhaps using whatever fairness constraints that you have determined, right? Now, again, the labeled data set will be biased due to partial feedback from the past or historical decision-making biases. So we don't have very complete information about the whole domain. So what we're going to do is we're going to divide our domain into an explore side, which is a side that we do have good information about. We have high confidence on the accuracy of what our classifier can predict there. And the rest is going to be on what we are calling an exploit side, and that's a side where we don't really know enough. So then we can look at our batch of applicants, and we again just divide this domain into two parts. we look at the applicants that are in our exploit side of the domain, and we consider those separately from those that are in the explore side of the domain. So for those that fit in this exploit side, we have high confidence in those decisions, so we can go ahead and just use our classifier. For those that are on the exploit side, we don't have that high confidence, so we're going to use a different method to decide when to classify them positively or negatively. Now again, same as here we're plugging in your classifier of choice. Here, precisely which strategy you might want to choose will be highly domain specific, but we can choose, and we give a few different examples in the paper, but in general what you'd want to do is choose something that still, that kind of balances maximizing information gain while also maintaining your suggested utility given what you know so far, which admittedly is incomplete, right? So that's why we're adding some additional exploration there so that we can continue to gain information about parts of the domain which we may not have ventured to try without this. So what we can show is that when we look at this type of high-level framework, if we consider, so we let f opt alpha be our optimal classifier that has highest utility, subject to having a pre-specified false discovery rate alpha, so we can consider that optimal classifier overall. Under mild assumptions, as we go through our iterative process, the utility of the classifier that we have learned along the way, as we go forward, will converge to the utility of that optimal classifier. So this rate of convergence will vary, and again, we give a few different examples in the paper, but really it depends, perhaps unsurprisingly, on what method we chose for that G, that explore side of the classifier. So for example, if we chose a G that just said, everyone here, we're going to give this entire set and classify it positively, well, that would give us a lot of information. We can do that for a few rounds. We're going to converge very quickly. Again, that may or may not be what you can or would be willing to do. So if you then again are very restrictive and say, okay, I will do a little bit of exploration, but I really want to primarily stick to what my classifier would predict so far, then you're not going to learn as fast, right? So you have to again balance these two often conflicting constraints to see how you proceed. And once you have some information given your classifier G, you can quickly draw out what your convergence rate is going to be. So another thing that we show is that we can also use any user-specified constraint on the number of false positives that we're kind of willing to tolerate. So we can also give you kind of a method to establish this G when you specify just how many false positives your system can tolerate, right? And so we do have a way to kind of help you choose what type of classifier G you might want to consider. So what this helps you ensure is that you have that high iteration-wise utility, right? While overall, again, you're still learning about the entire space and converging to an optimal classifier overall. Okay. So we looked at the adult data set to do an empirical analysis of this work. We consider a couple other data sets as well. I will just show you the results for this. Many of you are familiar with this data set. It contains demographic and financial data of about 250,000 individuals from California, and the task was to predict whether the annual income is higher than 50K or less, and we considered a binary race, white or non-white, for this data set. This is kind of a standard benchmark that has been used in many different things. It is not perfect, of course, as no data set is, but this is a kind of proxy for various financial decisions that can be made. So this is the data set I will show you the results for today. And for the results I'm going to show you, I'm going to show you a few different cases where we consider classifiers with some kind of fairness constraint, in this case, disparate impact constraint. And for our framework overall, we actually have 2 different points where we can step in and enforce some kind of fairness. So we could either have chosen a fair classifier at that first exploit stage, right? So that's one place where we can put a fair classifier. We could also enforce fairness constraints in the, what I was calling G, right? So in the explore phase. So these are 2 different intervention points where we could consider what specific fairness goals would be and intervene there. Or, of course, we could do both or neither. So in any of these cases, what we see is that as we have more and more iterations, the true positive rate is going to increase, and it increases both for black applicants as it does for white applicants. So it will increase across, it will increase for both black applicants and for white applicants. The difference, I don't have a pointer, the difference between the blue line, that is no fairness constraints, versus the either one or both types of fairness constraints, that gap is what we would consider a kind of fairness gap, as is often present when you place more constraints on the system. We expect the utility to perhaps be reduced, but we see that in any of these cases, we are learning, right? If we were not doing this exploration, we would stay this at the 0 iteration because that is what our initial classifier would say, right? So we're dramatically increasing the true positive rate for all applicants overall by using this learning process. So in particular, so again, this is iteratively increasing. We have a high per iteration utility. We don't have a high upfront cost, and overall we're converging to the optimal solution. In our paper, you can also see we compare against other prior approaches, and you see that that you can see this empirically as well. So overall, we provide this framework for data collection and learning. We get the high prediction utility in every iteration, and we're able to gather that outcome data for what were previously unobserved samples. And we can focus both on the short-term gain and that long-term utility by balancing both of these explore and exploit sections of our domain. So overall, I would say that fairness can and should be incorporated in both of these areas at once. Again, the specifics of how and where you would want to implement that would be completely domain specific. So thank you. I'd be happy to answer any questions.
Thank you, Elisa. We have time for a couple of questions from the audience. Okay, we have a question here.
Thanks, Elisa. One clarifying question. How does FT affect G? How does G affect the next iteration F? Is it in terms of how you do the explorer versus exploit split?
Yes.
And second question is, your null constraint, fairness constraint, seems to keep increasing utility, whereas the explorer and exploring exploit seems to flatten and converge. Is that a reflection of this sort of beta trade-off between max, I just wanted to sort of focus on the stability, the convergence versus the increase. Thank you.
Okay, yes, thank you. So for your first question, oh, I lost it. Okay. So your first question, what happens is, so we split the applicant pool, right? So we did our exploration to classify our G exploration step to classify these set of applicants. So all of that information is then going to feed back to our next FT, right? And the point is that for most of the people in this exploit group, we would never have classified them positively if we just used the original classifier, right? So this is what's forcing us to explore or to test part of that domain that previously was just automatically funneled into reject or into negative classification because we simply did not have enough information about that part of the domain, right? So it's forcing us to look more broadly than the data we have would have initially asked us to do. Is that? Make sense? Okay. Now about the results. Yes, I see it looks like many of these are flattening out while the blue curve is increasing. I probably should have given you a few more iterations. That blue curve also levels out. And again, yes, that gap is just due to this inherent utility fairness trade-off.
Okay, some final question or comment? Okay, we have two who raised their hands quite at the same time. I'll start here. If you can please make it quick, just in the name of time. Otherwise, we can take the discussions offline.
Yes, my question is more of a clarification question, because you mentioned the fairness classifier is like agnostic. How much of the Explore framework relies on group information? Like, do you need Z, like the sensitive attribute?
I guess for the applications that I've been thinking about, we use Z. You wouldn't necessarily have to use Z, right? It is something that just, again, forces you to explore part of the domain that you don't have information about. So this is useful generally. But yes, specifically for what we looked at and the experimental results that we ran, we were assuming we had Z.
And it was, you're right.
Yeah, so I'm wondering, in order to do things like decide where in the space you have enough information to exploit or to offer like iteration-wise guarantees about false discovery rates, do you need something like that the models are well calibrated in some sense, right? Like you know like when you know and don't know things.
Right. So there's different approaches on how you would do that partition. So one would be if you are using some kind of classification approach that gives you some kind of confidence, you could just simply use that. Otherwise, what we've done is looked at just the data itself and taken a look at you can basically partition the data based on where you have patches where you don't have any information. Right, so you can either focus on the data itself and do your partition that way, or use a classifier that gives you some kind of confidence and partition it based on that.
Thank you everyone for participating. Let's give another round of
Thank
applause
you.
for Elisa.